You are given an array of unique numbers that originally covered every value in some range. But a few numbers in the middle got removed, though the smallest and largest values are still there. Your job is to figure out and list, in order, exactly which numbers are missing from that range. If nothing's missing, just return an empty list. Beginner level, here's the setup. You're given an array of numbers, no repeats. Imagine it used to hold every whole number, from the smallest one up to the largest one, no gaps at all. Now some numbers from the middle are missing. Your job is simple to state. Figure out exactly which numbers are gone and give them back sorted from smallest to largest. This kind of find the gap problem shows up a lot in real software. Missing IDs in a database, skip invoice numbers, drop network packets. It's also a very common first interview question, so it's worth learning well. Don't worry if the trick feels new right now. By the end of this video, you'll recognize it instantly. Let's not think about code yet, just look at one small example. Say nums is 1, 4, 2, 5. The smallest number here is 1. The largest is 5, so the complete range should be 1, 2, 3, 4, 5. Now check each number in that range against our list. 1 is there, 2 is there, 3 is nowhere to be found, 4 is there, 5 is there. 3 is missing. That's the answer we're aiming for. Before we write anything, let's meet the 4 built-in tools we'll lean on, each one explained on its own first. Min of nums and max of nums just hand you the smallest and biggest number in a list. Min of 4, 2, 5 is 2. Turning a range into a list builds an actual list of numbers 1 through 5. A range on its own is lazy and doesn't show numbers until you wrap it in list. App strips away a negative sign, apps of negative 3 is 3. That's it. And a list comprehension is just a compact loop that builds a new list by keeping only the items that pass a test. Like keeping only the items that pass a test, like keeping only the numbers greater than 1. Min does numbers until you wrap up the most natural first idea. Loop through every number from smallest to largest, and for each one ask Python is this number inside nums, using the in keyword. This absolutely works and it's easy to understand. The catch is that checking is x in nums on a plain list has to scan the whole list each time, which gets slow for big inputs. You could speed that up with a set, but then you're spending extra memory just to hold that set. Let's look at a smarter way that avoids both problems. This is the key idea of the whole video, so let's go slow. Instead of asking a set, have I seen this number, we build one small array called tracker, where the position in the array tells us which value belongs there. Slot 0 holds the smallest number in the range, slot 1 holds the next one up, and so on. So if low is 1, slot 0 is meant for the number 1, slot 1 is meant for the number 2, slot 2 is meant for the number 2, slot 2 is meant for the number 2. In other words, the index itself acts like a lookup table. We don't need to search anything, we just jump straight to the right slot using simple subtraction. That's what index as hash have eyes means, and it's the whole trick this video is built around. Here's the plan in plain English. 2 simple passes over the data. Pass 1, walk through nums, and for every number we see, go to its slot in tracker and flip the sign to negative. That's how we mark this one showed up. Pass 2, walk through tracker again, and any slot that's still positive was never visited, meaning that number never appeared in nums. We only need that one tracker array, nothing fancier. Let's watch this happen step by step. Each number in nums goes straight to its own slot and flips it negative. No searching involved. First one flips slot 0, then 4 flips slot 3, then 2 flips slot 1, then 5 flips slot 4. Keep your eye on index 2, it never gets touched by any of these flips. Hold on to that thought for the next slide. Now that marking is done, let's look at what's left. Index 2 is still showing 3, positive, untouched. Every other slot got flipped negative because its number appeared in nums. So the rule is, positive means nobody ever visited this slot, and that means the number it represents is missing. That's the payoff of doing all that sign flipping. Let's turn the plan into code, line by line. First we grab low and high using min and max, the edges of our range. Then tracker gets built from a range of low to high plus 1, giving us the actual array of values from low to high. Remember we need the plus 1 because range stops just before its second number. Then for every num in nums, we take num minus low to figure out which slot that number belongs to, and we flip it negative. We wrap it in abs first so that if the same number somehow got processed twice. Flipping a negative back positive by accident can't happen. Abs always makes it positive before we negate it fresh. One line finishes the job. This is a list comprehension. Remember from a couple slides back, it's a compact loop. For every val in tracker, keep it only if val is greater than 0. Those surviving values are exactly the numbers nobody marked, meaning they were missing from nums. And since tracker was built in order from low to high, the result comes out already sorted. We get that for free. Here's the complete function, all in one place. Every single line here you've already seen explained piece by piece, nothing new is hiding in here. If any line still feels fuzzy, that's completely normal. Go back a couple slides and watch that part again before moving on. The line most people trip on is num minus low. So let's plug in real numbers slowly. Say low is 1 and num is 5. Then 5 minus 1 is 4, so the number 5 belongs in slot 4. Now say num is 1, the smallest value itself, 1 minus 1 is 0, so 1 belongs in slot 0. On belongs in slot 0. All this line is really doing is asking how far is this number from the start of the range. That distance is exactly which slot it should land in. Try it yourself with num equal to 3 and low equal to 3 and low equal to 3. And low equal to 1, you should get slot 2. Let's trace the whole function by hand with nums equal to 5, 1. First, low is the minimum, 1, and high is the maximum, 5. Then tracker starts as 1, 2, 3, 4, 5. Now we loop through nums. First num is 5, 5 minus 1 is 4, so we flip slot 4 negative. Tracker becomes 1, 2, 3, 4, negative 5. Next num is 1, 1 minus 1 is 0, so we flip slot 0. Tracker becomes negative. 1, 2, 3, 4, negative 1, 2, 3, 4, negative 5. The loop is done. Now we collect whatever is still positive, 2, 3 and 4. 4, so we flip slot 4 negative. Tracker becomes 1, 2, 3, 4 negative. Tracker becomes 1, 2, 3, 4 negative 5. Your turn. Pause the video here. Nums is 7, 8, 6, 9. Work out low, high, build the tracker on paper and flip each slot by hand just like we did last time. What do you think comes out the other end? Here's the answer. Low is 6, high is 9. So tracker starts as 6, 7, 8, 9. Every one of those 4 numbers, 7, 8, 6, 9 is already in nums. So every single slot gets flipped negative. When we collect the positive ones at the end, there simply aren't any. So the function returns an empty list, meaning nothing is missing. That's the correct clean result. Here's a real bug I hit before. I once assumed the range always started at 1 and used the raw value as the index, no subtracting low. That silently breaks the moment low is say 50 instead of 1 because tracker doesn't have 50 slots. The fix is always subtracting low before indexing like we did. Also double check the tracker size. It needs to be high, low plus 1 slots, not high, low. Forgetting that plus 1 is a classic off by 1 mistake. There's a much simpler looking alternative using a set. Set nums turns your list into a set, which makes checking membership fast. Then we loop the full range and keep whatever is not in scene. Only 3 lines, very easy to read. Honestly, for a quick script, I'd probably reach for this version. It's obviously correct at a glance. The tracker trick from earlier only really pays off when you specifically want to avoid the extra memory that a set uses. Let's talk about speed and memory in plain terms. We touch every number in nums once to mark it and every slot in tracker once to collect it. Both of those are single straight through passes, no nested loops. That's what big O of N means. The work grows in a straight line with the input size, not faster. And since tracker doubles as our answer, we never build a separate hash set, so we are not paying extra memory for lookups. Let's quickly check this handles the edge cases. If nothing is missing, we already saw it correctly returns an empty list. What if the array only has 2 numbers, just low and high themselves? Tracker would have 2 slots. Both get flipped and we get an empty list back too, still correct. And since the problem promises every number in nums is unique, we never have to worry about the same slot getting flipped twice by accident. Remember that one slot from the marking animation that never got touched? Now you know exactly why that mattered. It was the missing number hiding in plain sight the whole time. To recap the whole idea in one sentence, the index acts as your lookup. The sign acts as a have I seen this flag, and whatever survives positive at the end is your answer. If you follow the dry run and the pause challenge, you've genuinely got this pattern now. New daily drops tomorrow, same time. That interview question is brutal. The like and subscribe buttons aren't. If something felt confusing or you want to see a topic explained, tell me in the comments.